Today we are solving 0, 1 matrix problem. Given an M cross N binary matrix, return the distance to the nearest 0 for each cell. They also mention the distance between two adjacent cells is 1. So in this example, in order to find distance of the nearest 0 for each cell, we only process non-zero cells, because the cells that are already 0, the distance to the nearest 0 is 0 itself. So let's first fill this distance matrix with zeros for all the cells that are already 0. Next, we process the non-zero cells. For example, the cell at the center of the matrix. The distance to the nearest 0 is these three adjacent zeros at distance 1. So we fill 1, and for the cell here at the bottom left, distance to the nearest 0 is again 1, and it's that cell. So we fill 1. Same goes for the bottom right cell. Distance to the nearest 0 is also 1. And finally, for the last cell, distance to the nearest 0 is not 1, because there is no immediate adjacent 0 cell to it. So the nearest 0 for this cell is either this or this, and both of them are at distance 2, so we fill 2. How would we go about solving problems like this? The hint for that is again in the question, where asking us to find the nearest distance. Anytime we have to find nearest or the shortest distance, if we can convert this given matrix into a graph, then we can apply breadth first search algorithm to find the nearest 0 cells. So how would we convert this matrix into a graph? So the graph has two components, nodes and edges. So nodes are straightforward here, where each and every cell would be a node in the graph, and each cell has its row index I and column index j. So that's our node. And edge, distance to the adjacent cells. For example, edges to this cell are this cell has 3 edges because it has 3 adjacent cells. So these act as edges. So now, how would we apply BFS to this problem? So here is another toy example, and let's look at how to apply BFS for this problem. So for each and every non-zero cell, we have to find the nearest 0. For example, if we start BFS from this non-zero cell, we would find that the nearest 0 can be reached using these 3 paths. And the third one is obviously this. So the BFS would discover that the nearest 0 is at distance equal to 3. So we could repeat that for each and every non-zero cell, and we would be able to find the distances to the nearest 0 for all the non-zero cells. So the complexity would be to run BFS on one non-zero cell, the runtime would be of mn, which is the size of the matrix, and we repeat this for each and every non-zero cell, and the worst case would be every cell would be non-zero. So this is the runtime complexity if we ran BFS individually for each and every non-zero cell. To kind of reduce this complexity, we can also run BFS in parallel for all the non-zero cells. We can start from all the non-zero cells and run BFS in parallel, which would reduce the runtime complexity to just O of Mn. For me personally, it is kind of easier to understand this algorithm if we went the other way around. Instead of finding distance to the nearest zero from each and every non-zero cell, we can find the distance from the zero cell to the nearest non-zero cell. So let's clean this up a little bit. This zero, how would we find distances to the nearest non-zero cell using BFS? So first we identify all the non-zero cells and add them to the queue to run BFS in parallel. So I've already pre-filled the distance matrix from that zero cell to all the other non-zero cells. So since we haven't started BFS yet, the distances to all the other cells is infinite. We explore all the adjacent cells to the current cell, these 4, and update the distances to those 4 cells. And the new distance matrix would look something like this, where we have the distance matrix now has distances 1 to all the adjacent cells. In this distance matrix, all the cells that are circled are now in the queue. So those are all the distances to the nearest non-zero cell. So now, since we have already completed exploring the cell, we can mark it as done. And now head of the queue has these 4 cells. So let's run the second round of BFS on all these cells. This is what the distance matrix looks like after round 2 of BFS. All the nodes that are circled are in the queue, and we mark all the explored cells as done. And we repeat this for one more round. The distance matrix looks like this, and all the cells that are circled are in the queue, and we mark all the explored cells as done, and we repeat BFS for one last time. And there we go. That's our distance matrix, and the cells that are circled are in the queue right now, but since these are all the edge cells, there is nowhere else to go. We can easily say that we have explored all the possible paths, and this is our final answer. Now let's write some code for this. The given matrix has m rows and n columns. Let's call them m and n. Next, we have to return the distance to the nearest zero for each cell. Let's call this matrix distance, and it has the same dimension as the given matrix. So we initialize with infinite because we do not know the distances to the nearest zero in the beginning. So let's initialize to infinite. And for each cell whose value is 0, we know the distance for the distance to the nearest 0 for those cells is 0 itself. So let's update those distances in range m, j in range n. If matrix of I and j is equal to 0, then we update the distance to that cell as 0. And then we have to put all of these cells into a queue, because from these cells we'll be running BFS in parallel. So let's define a queue here. Okay. Next, we run the BFS for all the elements in the queue in parallel. So while queue is not empty, since we are running BFS for all the elements in parallel, let's just see how many elements are there in the queue. And for all the elements in the queue, we get the row and the column by popping elements one by one. And now to run BFS, we need to explore all the adjacent cells. So for X and then Y will be the next X and Y. And we need to look at the 4 adjacent cells to X and Y. That will be X plus 1, Y. That is one adjacent cell. X minus 1, Y is another adjacent cell. And the third one would be plus 1, Y minus 1. So these are the 4 adjacent cells we need to explore. So if they're out of boundary, for example, n x is less than 0 and y is less than 0, or nx is greater than or equal to m and y greater than or equal to n, these cells are all out of boundary. We don't need to explore them. And there's one more case where we can skip those cells, is if we already know the distance to the new cell is less than or equal to the current distance. Let's call this current distance 0, because when we add elements to the queue for the first time here, all of those cells have value 0. That means they're all at distance 0. So here, when we are exploring the adjacent cells, if the distance to that adjacent cell is less than or equal to the distance to the current cell plus 1, because we need to take that one step from the current cell to the adjacent cell. So if the distance is already less than or equal to that, we can skip those cells. If not, then we update the distance to the adjacent cell, the distance of the adjacent cell, to d plus 1, and then add them to the queue for the next round. X and Y. Once we have explored all the nodes in the queue in this current round, we increment the distance by 1 for the next round. So we repeat this until we have no more elements in the queue, and return the distance matrix. So that's our code. Let's try to run this. So it passes all the test cases and submit. So the runtime for this algorithm is big O of m times n, because we are exploring each and every cell. That will be every cell in the matrix. That's the runtime, and the space complexity is again big O of m cross n, because we have this distance array which is of same dimension as the given input. If you found this video useful, please like the video, and I will see you in the next video.